Hello and welcome to yet another lecture on permutations and combinations. In this lecture, we will be looking at a very powerful technique which can be used to generate several identities based on the binomial coefficients. And this technique is the technique of generating functions. So suppose you have a sequence A of real numbers, which is indexed by A0, A1, so on to AN, and so on. A generating function for the sequence A is given by the function GA of x equals A0 x power 0 plus A1 x power 1, and so on to AN x power n, and so on. So this is a generating function for the sequence A, and this can be more compactly represented by summation aj x power j, j going from 0 to infinity. So the reason why this function GA of x is called a generating function for the sequence A is because you can note that aj corresponds to the coefficient of x power j. So the jth term of the sequence can be obtained by just reading off the coefficient of x power j in this function GA of x. So to give you a very simple example for generating functions, let's consider the sequence NC0, NC1, and so on to NCn, and so on. You can consider the higher terms in the sequence to be 0 because you can at most choose n objects from n distinct objects. So NCn plus 1, NCn plus 2, and so on can be taken to be 0 for the purposes of this example. So the generating function corresponding to this sequence is given by 1 plus x the whole power n. For those of you who looked at the binomial theorem chapter, this is nothing but summation j equals 0 to n ncj x power j. So the jth term in the sequence, which is nc j minus 1, corresponds to the jth term of this sequence, which is given by the coefficient of x power j minus 1, and which is nothing but nc j minus 1. Sorry, the jth term of this series. So you can just get the coefficients of the sequence by reading off the coefficients of the powers of j in this function, and so the function 1 plus x the whole power n is a generating function for the sequence nc0 so on till ncn, and so on. So let's look at an application of generating functions towards deriving useful identities. So a reasonably famous identity in combinatorics is called Van der Mon's identity, and the identity goes as follows. It states that m plus n choose k equals summation I equals 0 to k, m choose I, n choose k minus I. So a combinatorial interpretation of this identity is fairly simple. So suppose you want to choose k objects from n plus n distinct objects. One way you can do it is you can choose I objects from m objects, and you can choose the remaining k minus I objects from the n objects, and multiplying these two gives you one way in which you can choose k objects from m plus n distinct objects, and then you just sum over all valid i's until and you get the desired result, which is nothing but m plus n choose k. So you can essentially see that this is counting the number of ways in two different ways. One is by directly counting the number of ways, and the other is using a summation. And this identity is very useful in many applications. So let's look at a generating function which will help you read this off. So m plus n choose k is nothing but the coefficient of x power k in 1 plus x the whole power n plus n. So m plus n choose k is nothing but the coefficient of x power k in 1 plus x the whole power m plus n, and so that's how you can get the left hand side of this equation. The right hand side of this equation can be obtained by looking at 1 plus x to the whole power m plus n as 1 plus x to the whole power m times 1 plus x to the whole power n. And once you consider these individual expansions and then you multiply them out, you can derive the right hand side as the coefficient of x plus x power k in this right hand side. So this is one way in which generating functions can be used. So since you know that m plus n choose k is the coefficient of x power k and 1 plus x to the whole power m, you can derive this identity by looking at a related generating function for m plus n choose k, and that gives you the right hand side of this identity. So before we proceed to our subsequent results, we need to know the following result, which relies on the binomial theorem for negative exponents. And so that says that the coefficient of x power r in 1 minus x to the whole power minus n is given by n plus r minus 1 CR. So this result can be obtained by considering the binomial expansion of this term, and note that n is a natural number here, so you need to consider the binomial expansion for negative indices to derive this result. So let's look at a first result which can be derived using generating functions. It says the number of ways of dividing n identical objects into R groups equals n plus r minus 1 C r minus 1 if empty groups are allowed, and this equals n minus 1 C r minus 1 if empty groups are not allowed. So we are considering the number of ways of dividing n identical objects into R groups, and depending on whether empty groups are allowed or not allowed, we have these two different results. So we can derive this result using generating functions, and we'll do so shortly. But before doing so, we have R groups, and we want to put these n identical objects in these R groups. And so suppose G1 is the number of objects in group 1, G2 is the number of objects in group 2, and so on. So we require that G1 plus G2 till Gr equals n. We need to put all of the original n identical objects into these R groups. So we want to find solutions to this equation, and in the first case we have Gj greater than or equal to 0. In the second case we have Gj greater than or equal to 1. So that's the distinction between these two cases. In the first case, empty groups are allowed, so Gj is greater than or equal to 0 for all j, and in the second case, empty groups are not allowed, so Gj is greater than or equal to 1 for all j. Right. So to derive this result, these results using generating functions, right? Let's consider the following function. So consider the function x power 0 plus x power 1, so on till x power n whole power r. So the reason why we are considering this function is as follows. So the exponent corresponds to the number of objects in a particular group, and this exponent r corresponds to the number of groups. So if you wanted to expand this out, what we would do is, let me just erase that properly. What we would do is we would write x naught plus x power 1 plus so on till x power n, and this product would be for a total of r times. And what this effectively means is that in the first group we could have 0 objects or 1 object or so on till n objects. In the second group we would have 0 objects or 1 object or so on till n objects. And in the final group we could have 0 objects or 1 object or so on till n objects. So the exponent in each of these functions denotes the number of objects in that particular group. And since we have r groups in total, we have r of these terms in our function, our generating function. So if you look at the coefficient of x power n in this function, that should give you the number of ways of dividing these n identical objects into these r groups. So each term which generates an x power n, if you notice, corresponds to a valid division of these objects into these r groups. And so you just need to consider the coefficient of x power n in x power 0 plus x power 1 and so on till x power n the whole power r. So this function is a generating function for this case, for the case of looking at the number of ways of dividing n identical objects into r groups where empty groups are allowed. And the fact that empty groups are allowed is represented by the fact that we have x power 0 in this function in each term, and that's because we can select 0, we can put in 0 objects in a particular group, and that's still a valid division. If we were not allowed to put 0 objects in a group, if all groups had to be non-empty, then we had to start our count from x power 1, because the exponent denotes the number of objects we are putting in that particular group. So the coefficient of x power n in this expansion is just going to be, let me denote it in shorthand by coefficient of x power n. This is a geometric series, and so you can sum the series up, which is what I'm doing right now. And this is what you get. And so you have the coefficient of x power n in 1 minus x power n plus 1 the whole power r times 1 minus x the whole power minus r. So this is what we have. We want to find the coefficient of x power n in this in the expansion of this term. So notice that any power of x, the only valid power of x you can take from the first term is just going to be x power 0. So we only need to look at the coefficient of x power 0 in the first term, because all other terms correspond to coefficients of x power greater than 0 in the first term. So we can ignore the first term, and since the coefficient of x power 0 is just 1 in the first term, we can ignore the first term altogether, and we'll only look at the coefficient of x power n in 1 minus x the whole power minus r. So once again, to repeat, all powers of x generated in the first term which are not 0 are going to be greater than n, and so the only relevant coefficient of only relevant exponent of x in the first term is going to be x power 0, and the coefficient of that term is just 1, and so we only need to look at the coefficient of x power n in this term. And for this we need to use our result on the binomial theorem for negative indices, which is given over here. So we want the coefficient of x power n in 1 minus x the whole power minus r. So notice that n and r are swapped from this result here. So we have to swap n and r, and so this is going to be nothing but r plus n minus 1 choose n, and this is nothing but using NCR equals NC n minus r. This is nothing but n plus r minus 1 choose r minus 1, which is exactly this result which we wanted to derive. So if empty groups are allowed, using generating functions, we can derive that the number of ways of dividing n identical objects into r groups is given by n plus r minus 1 choose r minus 1. So the second result can be derived in a similar manner by by looking at the coefficient of x power n in x power 1, so on to x power n whole power r. So we omit the term x power 0 since we don't allow empty groups in our division, and so we are only concerned with the coefficient of x power n in this expansion, and you can derive it in a similar fashion and verify that it turns out to be n minus 1 choose r minus 1. So let's look at a related result which says that the number of ways of dividing and arranging n distinct objects in r different groups equals n factorial times n plus r minus 1 c r minus 1 if empty groups allowed, and this equals n factorial times n minus 1 c r minus 1 if empty groups are not allowed. So this result is similar to the previous result, but in this case we assume that the groups are distinct and the objects are distinct as well, and we want to look at the number of ways of dividing these n distinct objects into r different groups and arranging them in these r different groups as well. So we are not going to derive this result, but a very simple interpretation of this result can be derived from the previous result, where first you assume that neither the objects nor the groups are distinct, and so you have these results carrying over. So we have n plus r minus 1 choose r minus 1 if empty groups are allowed, and n minus 1 choose r minus 1 if empty groups are not allowed. So once we have that result, now we reconsider the fact that these objects and groups are all distinct, and so every permutation of these n objects, every linear permutation of these n objects will give you a different permutation of these objects in the groups, different arrangement, and so we multiply just by n factorial to derive these results from the previous result. So look at a last result for this lecture, which says that the number of ways of dividing n identical objects into R groups so that each group contains at least p objects and at most q objects is given by the coefficient of x power n in the expansion x power p plus x power p plus 1 and so on till x power q the whole power r. So now we want to divide n identical objects into R groups so that each group contains at least p objects and at most q objects. So this is a generalization of this result we've seen earlier, where we have at least p and at most q objects, and so this result just follows in similar manner to our previous reasoning, where we start our terms from x power p since we need to have at least p objects, and we limit the terms till x power q since we can have at most q objects in each group, and we raise the whole thing to the power of r since we have r groups. And so we just have to compute the coefficient of x power n in this expansion and you can potentially derive a closed form solution to this by following an approach which we followed earlier for the simpler case. So that's it for this lecture. I hope you enjoyed watching it. In our next lecture, we will look at some examples of the application of these results which we have derived in this lecture. Thank you for your attention.